Welcome back to the Organic Chemistry Final Exam Review Part 2. If you missed Part 1, the link is in the description. If you watched Part 1, let's jump right in with a couple of warm-up reactions. For problems like this, if you see this on your exam, there are two ways to approach it. Sometimes students like to go through the mechanism, which is fine if you are asked for the mechanism. But if the problem just says complete the following reaction, you do not have time. You cannot afford to go through the step-by-step mechanism if you're not asked for it. And so any problem here that is not asking for a mechanism, I want to make sure that we're on the same page in how we approach the shortcut. And so we want to look at this problem. And again, this is an easy warm-up problem, but I want to make sure that the concepts can be applied to the harder problems. So it's about the approach rather than just the answer. I see a problem like this. I want to evaluate from the perspective of what is going on. With all of organic chemistry, if we had to simplify what is happening, nucleophile, which is highly electronegative, has a lone pair, attacks electrophile, something positive or partially positive. And so in any question, I want to ask myself, what is the most negative? What is the most positive? How does the most negative attack the most positive? And so in this case, I see my pi bond. Those are highly electronegative electrons. I see an HBr, which you should remember is a partially positive hydrogen, a partially negative bromine. And so if I did the mechanism, I would show the pi bonds attacking the proton, bromine breaking away, all of that good stuff. We don't have time for a mechanism. So if we identify that this is an electrophilic addition reaction, all I have to do is break the pi bond, redraw the skeleton exactly as I see it, and then ask myself, what exactly happened here? When the pi bond attacked the hydrogen, I had a carbocation intermediate. That carbocation has to form at the more substituted position, which means hydrogen adds less substituted, but we don't show hydrogen in the product. Instead, we know that with Markovnikov's rule, the nucleophile attacks where that carbocation used to be. And so my shortcut is to simply put the bromine at the more substituted position because this is a carbocation intermediate, therefore follows Markovnikov's rule. Afsana, I don't understand your question. For the next one, let's take a look at a molecule that looks like this. Your professor should never, ever, ever draw it like this. Yes, I've seen that before. An alkyne is sp hybridized at the carbons holding that triple bond. That means it's linear. And we're going to react it with HCl in excess. All right, so what is going to happen here? Just like with an alkene reaction, when the pi bond breaks, I have the H and the halogen both are going to add. And so in this case, because I know my pi bonds are going to break, I can redraw the skeleton no longer in a linear form. Instead, I can redraw it now as a zigzag because the carbons will be sp3 hybridized. And then the shortcut, because I know it's adding in excess, I break the first pi bond and I put an H and a Cl. I break the second pi bond, that H follows the H and the Cl follows the Cl. And so I get a geminal dihalide, a dihalide where both halogens are on the same carbon. And technically, you don't even have to draw the hydrogens. So you would show it just like this. I saw a question here. Whoops, I clicked on, I missed the question. I think it was asking for the stereochemistry. I was about to click it and the chat just scrolled on me. The first molecule that we did, this right here is a chiral carbon. And so we would have stereochemistry in the product. If your professor asks for the stereochemistry, recognize that because this undergoes a carbocation intermediate, actually it doesn't even matter about the carbocation. Because we're starting with an alkene, an sp2 hybridized carbon, trigonal planar, it's flat. And so the bromine can attack from the top or from the bottom, giving me 50-50. And so yes, the product is chiral, it will be racemic. I'll have 50% R and 50% S. I caught another question here. What if CCl4 wasn't there in the first problem? If you had a problem like this and CCl4 was not given, you have two different options. So let's move it down. Option 1 is if nothing is given, only HBr, then what we're going to do here is assume. And we're going to assume that the solvent is inert. The solvent is not going to react. So for example, CCl4, CH2Cl2, anything like that. And that will be the same exact reaction that I just showed you, following Markovnikov's rule. Same thing. I don't know why I drew that out twice. The other type of reaction that you can have here is if you're given HBr, but this time you're either told that it's a dark or a light reaction. We need more room, so you need to shut down a little. Thank you. Yes, I talked to my staff. If I'm given dark reaction, that's this one. That means we're not adding any intense light. But if I have HBr and I put something like light or heat or peroxides or anything that is going to imply a radical formation, it's going to be the complete opposite. Instead of a carbocation intermediate, I'll have the radical intermediate, and this will follow an anti-Markovnikov addition where the radical halogenation puts the bromine on the terminal carbon rather than the internal carbon, giving me a primary halogen. My nose. This is really useful for synthesis when you want to get a leaving group on the terminal carbon and you have something else going on. All you have to do is turn it into an alkene and then do a radical halogenation. So that was a really good question. Let me see. Okay, so then for the second problem, how come the chlorine adds to the same carbon? So this has to do with the stability of the intermediates as you're going through the mechanism. And the way that this works out is where you have the first chlorine is favorable for adding the second one to the same situation. What's the difference when a professor asks you to draw the major product and when he asks you to write the mechanism for the major product? If you're asked for the major product, you just draw this out. If you're asked for the mechanism, you have to show the individual step by step, the arrow, grabbing electrons, everything collapsing. So you'd have to show exactly how the electrons move to get you there. Bella, thank you so much. Looks like Bella is here to cheerlead and help. Bella aced her exam today, so definitely hit her up for questions. I assume that was okay to just volunteer you right there. If you were just joining or watching the recording, welcome. For a copy of tonight's session notes, as well as the notes for part 1, go to layforpsi.com/orgoalive. You'll get the session notes, practice worksheets, and so much more. Here we go. I lost my button to remove that. All right, so let's crank it up just a little bit. And for this next one, as I'm drawing this out and you see the ring, does that make this problem look scarier or still pretty good, pretty doable? What do you think? The reason I put this ring, and the reason quite a few of the additional problems have a ring, is because when you learn reactions, you tend to learn them like this. Pretty simple, pretty small molecules. And then adding a ring just makes everything seem so much more overwhelming. I want to show you that the ring does not make it scarier. The ring is just part of the molecule. And here's a trick. If you see a reactive portion and then a lot of things going on, rings and chains and substituents, and you're overwhelmed, just cover it up. It doesn't matter. We're just looking for the piece that is reactive. And in this case, it happens to be the pi bond and the carbons holding the pi bond. Nothing else really matters. So cover up the rest if you have to, and then only focus in on the piece you're working on. I'm not looking for the mechanism, so I have to think this through in terms of getting the reaction. What is the most reactive? I have these 2 pi electrons on the molecule. This will be an alkene addition reaction, and it will react with Cl2. Now, if I had an inert solvent like CCl4, or no solvent given, Then I would do a halogenation where I put one chlorine on the top, one chlorine on the bottom. But my solvent is not inert. And I guess I should have put over here, one more option is a solvent that bites its nose in for a solvolysis reaction, but we're not going to make that one too crazy. The CH3OH is going to react. And so when I have the first chlorine forming that chloronium bridge, the second one is off in solution, completely surrounded and distracted by the methanols. So I draw my skeleton, I break the pi bond, and I put the chlorine on just one of the carbons that used to hold the pi bond. I randomly chose to put it on a wedge. I could have also put it on a dash, same thing. But then for the other piece, it's not going to be another chlorine. Coming in for a backside attack is going to be the solvent. Now, what kind of reaction is this? That is a very good question. Where did it go? Here we go. This is what started out as a halohydrin formation, except a halohydrin is when you have the halo, which is the hydrogen, and the hydrin portion, which is an OH. Halo is not a hydrogen. Halo is a halogen. The X and the OH. But if we have something else in the solvent that is not water, but an alcohol, then what you're going to do is the backpack trick. So let me show you. If I have a water molecule, if this was not in methanol, if this took place in water, the way that you do this is for the piece that you add, you already know it's an OH, but I want to show you the backpack trick. You cancel out one hydrogen because that will be deprotonated. You add your electronegative atom to the other side, and then the backpack is anything else that's attached to it, in this case, an H. But in this molecule, the CH3OH is very, very similar. Instead of being HOH, it's HOCH3. But the way I add it is exactly the same. I deprotonate a hydrogen, cross it out, add the electronegative atom, which I already did, and then the backpack is whatever is left on the molecule simply adds over there, whether it be a CH3, an ethyl group, an isopropyl group, a whatever. It's just an oxygen carrying a backpack. That backpack can be big or small. It doesn't change how I approach this reaction. This would be one product, but because this started with a pi bond that was sp2 hybridized, I could have just as easily put my chlorine on dashes. And that means the second portion, the methanol, would have added on a wedge. What is the relationship between these two products, which are both equally going to form? Yes, this is technically racemic in that we're forming one of this and one of that, although the stereochemistry is specific. It's not that I randomly put this and randomly put this. They have to be opposite to each other. This is an anti-addition, not anti-Markovnikov, anti in that one adds to the top and one adds to the bottom. And the relationship between them is that they are enantiomers, because every chiral center is exactly the opposite of the starting molecule. Where did the other hydrogen go? The other hydrogen got deprotonated, and so one of the methanols in solution would have grabbed it. We're not going to go through every mechanism today because we'll never get through all the problems, but I will do some problems later with mechanisms, so we'll practice something similar. Question, CH3OH turned into OCH3. So this is a question that comes up a lot, and it's really just a technicality. If I have a CH3OH and I draw it the other way, it could be drawn like this, right? Do you see how this is the same exact molecule? I have two ways to draw this. I can write this as HOCH3, or I can write it as HOH3C, because technically it's H3 and then the C. Now it looks a little bit weird the way I have it drawn like this, but if it's drawn on something, it's not uncommon to see it drawn as the H3C. We're spinning things around, but it's the same thing. Really, really good question. So this is a halohydrin, except we're using an alcohol rather than water to get different product here. So in a halohydrin, you get an alcohol on there. In using an alcohol, you get an ether. So this is an ether because we started with an alcohol. Question, why does the solvent take part in the reaction? Very, very good question. If we have an inert solvent that doesn't react, that solvent just does its thing and acts as the solution. But when you have something that is highly electronegative and polar and capable of hydrogen bonding, if we form a Cl- in solution, this Cl- is going to start attracting all of the partially positive hydrogens from the methanol solution. And so as all the partially positive hydrogens surround this, this is now no longer available to react because it's partially positive, partially positive, partially positive. It's fully stabilized by a counter charge, and so it has no ability to react. And if it has no ability to react, well, another methanol in solution happens to notice that our intermediate has a partial positive charge, and it will attack because it's an opportunist and it's going to just attack when it sees a positive charge. All right, I see more questions coming in. Let's do a few questions per, and hopefully as we go through more and more practice, more things will start clicking into place. So first things first, are you feeling nice and warmed up with the few initial problems? I think we are. I'm starting to feel warmed up. If you haven't already, make sure that you subscribe to my channel. Let me try to say that in English again. Make sure you subscribe. I don't know what word I just said. And then let's try a problem that is given backwards, where this time we have to come up with a starting molecule, given that the reaction conditions are as follows. In the presence of Cl2, I form a molecule that has a chlorine like this and a chlorine like this. It looks like it should be a pretty straightforward reaction because I have my product, I have my reagent. What molecule will react with Cl2 to give me 2 chlorines on the product? Well, those 2 chlorines will add to a pi bond. But I can't just start drawing any pi bond because the stereochemistry here is very specific. And with this stereochemistry, knowing that this is going to do an anti-addition, not anti-Markovnikov, anti in that 1 chlorine adds above the pi bond and 1 adds below. My question to you is, am I going to start with a transalkene or am I starting with a cisalkane? And this is not something I want you to guess. This is something that you really have to know. Well, how do we know? In this case, I think the molecule is clear enough that you can guess, but I want to show you a trick just in case it's a little bit harder, a little bit more confusing, and I want you to very easily be able to figure it out. And that trick requires a little bit of knowledge of cars. Specifically, we're looking at a car called a Trans Am. I used to teach the car trick, and then one of my students named Russell told me about the Trans Am, and the whole shortcut just fell into place. And this is what I want you to memorize. CAR stands for cis, anti, racemic. And the Trans Am tells us that if it's trans, anti, it will be meso. So what does this mean? If I have a cisalkene, and I do an anti-addition like Cl2, my product will be racemic, meaning 1 will add forward, 1 will add back, and I'll have the enantiomer of it as well. So that's for the first one, for car. If, on the other hand, I start with a transalkene, and I do an anti-addition, for example, Br2, Cl2, same thing, now the product will be meso. So if I draw it out looking like this, I'll have the bromine here and the bromine here. How is that meso? I have a line of symmetry going down the middle. But these are supposed to add anti. So how does that work? Well, if I take this molecule and I keep the first half steady, but I rotate the other portion 180 degrees, look at what happens. This part of the molecule is steady. Then the other part rotated, so I have it like this. That is an anti-addition, one added above, one added below. Now, if I take this one, just to show you what it looked like if I draw it the other way, and I do a partial 180, this part of the molecule stays the same. This part of the molecule rotated, and now I get this. Notice this is not meso because the symmetry, you have to turn it. It's not a perfect mirror image down the middle. And so when you're given a molecule in this form or this form, recognize that you can turn it. And then based on what you're given, you can solve it like this. So first, let me know if this is clear, if this makes sense. And then I want you to ask yourself, well, what if I don't have the ability to do a meso because there's no perfect symmetry? So for example, I can apply the same trick to, say, a molecule like this that is also trans, but it can't ever form meso because it's not going to be perfectly symmetrical. And in fact, let's do Br2 and H2O. The product in this case, if I draw it out like this, we'll have one going forward, one going back. So what does this have to do with meso? It looks like absolutely nothing, but I want to show you what happens if I rotate it and I pretend that the substituents are the same. What I'm looking at with this idea of the meso shortcut is that if everything were equal, we can pretend if this was the same, it looks like it would try to be meso. So that is how this works, even when the substituents that you add are completely more complicated. So hopefully this makes sense. If you have any questions on this, let me know. And then let's go back to here. Given that I have a perfectly symmetrical product, this is a meso compound. And because it did an anti-addition, I will use the trans M and say that an anti-addition for a meso product started trans. That's my starting molecule. That is not my starting molecule. And I didn't have to do a whole lot of guesswork. There will be no enantiomer here because a meso compound has an internal plane of symmetry. If I flip the molecule, it'll be exactly, if I switch the chiral centers, it would be exactly the same. Question, can you use an alkyne and hydrogenate via Lindlar and then react via Cl2? You can, but wait, why would we want to use Lindlar? Because Lindlar would give us this, and we just ruled out the cis alkene. So it can't be Lindlar. But if I gave you a product that looked like this, then yes, you could have done that. How is it anti if both CLs are wedges on the product? That is a really good question. Both CLs are wedges because I rotated this way on purpose to trick you. But as I showed you here, if I have something that looks like this, there is free rotation around the carbon-to-carbon bond because there are 100 and, wow, my brain just froze there. It's sp3 hybridized, 109.5. They can rotate and rotate. And so this is what it would look like. But if I rotated, this is a tricky way to show it to you. And of course, professors are not going to give you the easy way. They're going to show you the tricky way to make sure that you picked up on the trick. And so this is really what we're dealing with. But if the molecule rotates, it will look that way. And so when you see anti-addition, but the two groups appear to be the same, they appear to be next to each other, just recognize it had twisted, and therefore it had to come from trans so that it can add anti and then rotate to give you this product. Really good question, Selena. Let me know if that makes sense. Fleur, we're going to get to that. Definitely going to get to that. So hopefully you're starting to feel better with the individual reactions and the pieces behind it. Now, as we go through more practice and you pick up the tips and tricks and shortcuts and you want to apply it, Make sure that you know how to practice them all together with my brand new synthesis exam. This is not available on my website. I just wrote it last week. Just comment synthesis and I will link it to you. Yes, even if you're watching the recording. Let's try another one using this trick where we have to come up with the correct starting molecule that when reacted with Br2 and H2O will give me this for the product. If you look at the product and notice that you have an alcohol and a halogen, that's a halohydrin. We have the conditions for a halohydrin because it's Br2 and H2O. That means we have to start with an alkene. But the question is, are we starting with a cis alkene or a trans alkene? So let's draw them both out and consider. If a trans alkene, I have my pi bond right there. And if a cis alkene, I have to turn it this way for a pi bond right there. Now I can manipulate the molecule and do all sorts of visual gymnastics to try to figure it out. Or I can look at this and say, this right here should be an anti-addition. If I have a cis starting molecule, anti gives me racemic. Well, this right here, because they're both on wedges, but they're opposite, this is along the lines of a racemic addition. Meso, they would have to be together and both wedges or dashes. The fact that they're opposite and both wedges or both dashes means it's a racemic type addition. And so cis anti-racemic means that this is my starting molecule, not this, so we cross it out. To see it, not that I want you to draw this on your exam, but I want you to trust the shortcut. Let me show you what happens. If I take this cis molecule and I react it exactly as I see it, I will get two products. I'm only going to show you the one that I drew. You could have also had the OH and the Br switched. And that's because the carbons holding the pi bond, meaning the sp2 carbons, are both the same degree of substitution. In this case, if I added the bromine here, the OH would have added like this. This is how you would draw it if you were asked. But then if you do a partial rotation, and specifically we're rotating here 180 degrees, this is what it would look like. You don't have time to do this on your exam though. And so you look at it and you say, these look racemic for an anti-addition, cis anti-racemic. That means it had to start as a cis pi bond. Typically, if you ever see a halogen like Br2 or Cl2 as a reagent reacting with an alkane, it's going to be anti-addition. Yes, exactly. Because the bridged intermediate is sitting there like this and nothing else can get through, it has to go around from the other side. All right, if you're just joining us, this is an Orgo 1 pre-finals reaction review. So we're looking at reactions that you'll typically see in Organic Chemistry 1. So let's take a look at, well, you tell me, do you see this as an easy, medium, or difficult problem? When we're reacting this alkene with D2 in PD over C. What do you think? Easy, medium, or hard? The thing about this reaction is it's very easy, except everything looks a little bit different than you're used to. And so I want to make sure you know exactly what to look for. Professors love to use deuterium for two reasons. One, to make sure you know how to follow a reaction, or for stereochemistry. What is going on? Something just popped up on my screen. Shoot, go away. So in this case, this is a straightforward halogenation reaction. Oh, I'm sorry. I asked what is deuterium, then I got distracted. So deuterium is just a heavy isotope of hydrogen. If you take a proton plus an electron and you put them together, you get a hydrogen atom. It has a mass of about 1 atomic mass unit, given that the electron has negligible weight and the proton is about 1. But if you take this same setup, you have 1 proton plus 1 neutron, which is neutral, plus 1 electron, which has 0 or near 0 mass. It's like an 1800th of an AMU. You're going to get a heavy hydrogen where it's about 2 atomic mass units. And if you know how to say 2 in quite a few languages, it kind of sounds like D for deuterium. You have de, dos. What other language has 2 that sounds kind of like the do in deuterium? So the 2-AMU, this is called deuterium. And anytime you see deuterium, just think it's hydrogen, but my professor wants to make it hard. That's really it. That's it. It's not doing anything else here. In Greek, it's dio. Cool. I just learned a new word. And so the shortcut for drawing the product for a hydration reaction, we draw the skeleton as we see it. We break the pi bond. Due in Italian. Cool. Learning new ways to say two today. We break the pi bond. And then we add both deuterium either up or down together. And so because I have a substituent on the molecule, I will have 2 products. I'll put the ethyl on a wedge first, and that means I'm adding the D on a dash, and that means this D is also on a dash. That's 1 product. For the second product, we'll squeeze it in over here. I'll put the ethyl, I'll just put it as ET for that ethyl group. And now I can put the deuterium on a wedge, and then this one also has to be on a wedge. Had I just used H2 here, then the only thing on this the only thing you would show for the product would be the ethyl group going up or down, and it would be the same thing. So the deuterium just makes it harder, and that is why professors like to throw it in. Do in Hindi. In Punjabi and Hindi, it's awesome. So this is my brain just had a brain fart. This is, it's going to say hydration. Hydration is water. What is the name of this reaction? Someone help me out. I'm stuck here. My brain is just completely frozen. Hydrogenation, right? Because there's a hydrogen in the word. How can I forget that? Thank you, Bella. See, Bella is just on. That is why Bella aced their exam. Hydrogenation. The reaction of hydrogen. I'll remember halohydrin, but I won't remember this right here. It's been a long day. Can you tell? All the names sound the same, yes, but you have to break down and see the words in the name to get it right. So how about we go away from the easy problem that I clearly have trouble naming and try something a lot more doable. You have a starting molecule. Let's go on the next page. That looks like this. C9H10. And in the presence of ozone, for ozonolysis, you are given 2 products that look as follows. What reaction am I looking at, and how would I approach it? Easy. I like it. More easy. Okay. See, that's what I'm talking about. Students are ready for their exam. In a situation like this, if I have ozonolysis that is going to cut everything at the pi bond, then I have to find a way to put them back together. But I want to have a general idea of what I have. The shortcut for ozonolysis is if you have a pi bond, you just cut it in half and put an oxygen there. So that's where all these oxygens come from, pi bonds that were cut in half. But let's use the starting molecule to get an idea of where we're going with it. I have 9 carbons, so I'm going to use the formula CN H2N plus 2 to figure out how many pi bonds or rings I have in the molecule. And this is one specific type of oxidative cleavage using ozone. There's a couple of different types that you'll learn. If I have 9, N equals 9, then H should be 2 times 9, which is 18, plus 2, which is 20. I only have 10. So what does that tell me? The difference between 20 and 10 is 10. Each pi bond or ring is missing 2 hydrogens. So we divided by 2, and that means I have 5 degrees of deficiency. I have a combination of pi bonds and rings that add up to 5. So looking at this molecule, if these are my 2 products, then these are all pi bonds cut in half. I should have a total of 3 pi bonds. That means I should have 2 rings. That is how I get a deficiency of 5. And let's see how we can figure this out. The best way to solve a problem like this is to literally stack them on top of each other. But this one is facing the wrong way. So what if I take the blue one and I redraw it 1, 2, 3 like this? Okay, so all I did was flip this one. Notice that I have my carbons 1, 2, 3, 4, 1, 2, 3, 4. Then I'll take this one and see if I can line it up underneath. I'm going to have to play with it just a little. But look how quickly and easily everything perfectly falls into place. So I have 3 pi bonds that I cut like this through ozonolysis. And if I draw it out, I have 1, 2, 3, 4 already numbered, 5, 6, 7, 8, 9. All my carbons are present. And if I try to clean it up, notice that I have a 6-membered ring right there. So I'll draw out a 6-membered ring. That represents carbons 2, 3, 4, 5, 6, and 7, with a pi bond between 4 and 5, another pi bond between 2 and 7. Then coming out of it on the other side, I have 1, 9, 8 attached back to 7. So that is 1, 9, 8 attached back to 7, 1, 9, 8, and a pi bond between 1 and 9, giving me my correct starting molecule right here. I hope that in watching me do this, you realize this was a very tedious, but maybe very, very easy or somewhat nearly easy problem. Professors are mean. I like that. And how did I get 2 rings? So let's go through the hydrogen deficiency one more time. To have a fully saturated carbon, I follow the formula CnH2n plus 2. This means every single carbon has a single bond either to hydrogen or to carbon with no rings, just a straight chain. In that situation, a 9-carbon fully saturated molecule would have a total of 20 hydrogens. And that's because I did CnH2n plus 2. And that was 2 times 9 because n is 9. That gave me 18. Plus 2 is 20. Then I compare it to the formula that I got. I got a 10. So a fully saturated molecule would have 20 hydrogens. I only have 10. Where did the other 10 go? So we have 10 hydrogens are missing. We know from looking at the products that I gave you that I have 3 pi bonds, and a pi bond has a cost of 2 hydrogens, and that means 3 pi bonds cost 6 hydrogens, but I am missing 10. So we have 4 more missing. And because we've already accounted for all the pi bonds, the 4 missing hydrogens must be in a ring, because just like a pi bond costs 2 hydrogen, a ring is also going to cost 2 hydrogen. And so 4 means 2 rings, 2 hydrogen for the first and 2 hydrogen for the second. I didn't see who asked the question, but for whoever asked the question, let me know if that's clear. And when one person posts a question, it's typically something that more students struggle with, but maybe didn't have a chance to ask the question, or watching the recording and will rather hear the question than have to type it in the comments. And so by voicing a question out loud, you're giving me an opportunity to explain something that other students also want to ask. So please, please keep the questions coming. These are really good questions. I still don't understand. Can we do another example? So let's do another example in reverse just to show you. Say I have a molecule that looks like this. and this. Okay, there we go. If I react this with ozone, the trick here is you break every pi bond, and on either side of the pi bond, you put in an oxygen. So that means for my product, I will start with, well, let's number it because this is going to be a little bit messy. This right here will be its own piece. So we'll call that carbon 1, 2, 3. No, that's probably not the best way to do it. It got cut here. So we'll call that 1, 2, 3, 4, 5, 6. It's a 6-carbon chain, which I'll draw out exactly as we see it. Carbons 1, 2, 3, 4, 5, and 6. Where on this chain, carbon 1 has an aldehyde, carbon 6 has an aldehyde, and carbon 3 has a ketone. The next piece of this molecule is right here. So we'll call this 7, 8, 9, and 10. That's this portion right here. And again, drawing it exactly as we see it, I have 7, 8, 9, and 10, where 7 has an aldehyde, 8 has a ketone, 9 and 10 have nothing. And then the last portion of the molecule is right here. That's just the 2-carbon chain. I don't even have to number it. We just do the 2 carbons right there and this piece right here. So these are all the pieces. Now, on an exam, it won't be given this pretty for this first one. It'll be given something like this, 1, 2, 3, 4, 5, 6. And then you'll have an aldehyde on the end, 1, 2, 3, a ketone here and an aldehyde here. And your job is going to be to figure out how to put everything together. Now, this would obviously make a much more difficult problem, but your professor will typically give you some kind of guide or direction or tell you, hey, go figure it out. What are the different options? So let me know if that clarified it for you. 3-ketone hexane dial. Ethanol should be 3 products. Okay, so you're naming the molecules. I didn't check them, but it sounds like you're either correct or very close. Destiny, excellent. All right, for this next one, let's see. We have a starting molecule. Someone asked for substitution elimination. So giving you fair warning, we are entering fun territory. The 2 biggest requests that I got is substitution elimination to cover tonight and ring expansion. So I am prepared with problems for both of them, starting with this right here, reacting with CH3OH and the presence of heat. Very simple problem. We just have to figure out the problem or figure out the product. Now, as much as the request came in for substitution elimination, we're going to do a few, and I tried to make them less than easy, meaning a little bit more difficult. But for even more practice, especially in choosing between SN1, SN2, E1, and E2 reactions, make sure you try my new substitution elimination midterm worksheet. I just created this a few weeks ago, not available on my website. Just comment SNE and I'll link it to you. Even if you're watching the recordings, just put SNE in the comments and I'll give you a link to download it. So where do we go from here? Remember earlier, I think it was the first problem, I said we want to approach the question with an evaluation of what is the most reactive, what is the most positive, what is the most negative, how is it going to react? And so in this case, I noticed that I have a molecule with a bromine sitting on this carbon. This is not very reactive, but I do know that this is partially positive. The bromine is partially negative. It makes a good leaving group, so I'm probably going to have a reaction in that direction. And then for my reactant, I don't seem to have anything. So I'm going to have to figure out what to do here. Recognizing that I have a leaving group, I have a polar protic solvent and heat, I see I'm going somewhere substitution elimination. And so we'll use the 4-part checklist to help figure out which reactions I can rule out between SN1, SN2, E1, and E2. And then whatever I'm left with is the reaction I'm going to follow. So the 4-part checklist that I teach in the substitution elimination series and videos that I've done before is starting with the alkyl chain. On the alkyl chain, I'm looking to see if I can form a carbocation, if anything is too hindered. And in this case, I see a secondary leaving group. It doesn't really tell me anything. So the next thing I'm going to look at is the attacker. The attacker will give me a clue as to what is going to react here. And is it going to be strong enough to kick anything out? Is it waiting for a carbocation? What is going on here? The problem is I have no attacker. So what is my reactant here if I'm not given anything? If there's no reactant given, but you see a polar protic solvent, this is a solvolysis reaction. Solvolysis is where the solvent is going to participate in the reaction. And we've already seen this in the halohydrin, right? The Br2, the Cl2, minding their own business, trying to react, and there the solvent goes and butts its nose in because it wants to react. Like my son, Mommy, what's in your mouth? Mommy, what are you doing? Mommy, what is... That's what this solvent is doing. It's just butting its nose into everything. And in this case, it is also going to be the attacker. Now it's neutral. It's not strong enough to kick anything out. And so we cannot have an SN2 or E2. Those are way too strong, way too fast. This is not strong enough. So we're left between SN1 or E1. And we'll move on to look at the solvent. It's polar and protic. It will stabilize any carbocation intermediates that form. Last, we look at the leaving group, confirm that it is a leaving group, a good leaving group, and it is. And so we're left with substitution and elimination. I can have both of them form, except that in the presence of heat, heat will help to stabilize the intermediates, and heat will ultimately help form more of the stable product. And so you will have competition between substitution and elimination, but elimination will give us the major product in this case. Unless you're asked for the mechanism, you don't have time to do the mechanism. Congratulations. Let's just take a quick interruption here. 20% above average, a 96. That is awesome, guys. Come on, let's all clap it up. That is amazing. Congratulations. Thank you for coming in and sharing this to give everyone hope and motivation to show that it can be done. Congratulations. So back to this reaction, we don't have time for the mechanism, so we're going to do it the faster way. Remove your leaving group. Redraw your carbon skeleton exactly as you see it without the leaving group, and then consider, if it's an E1 reaction, where does my pi bond go? If this right here is the alpha carbon, then the beta carbon here has one hydrogen, which I drew in green. The beta carbon here has two hydrogens, which I drew in light blue. And I can have products that form for both. But if we're looking for the major product, I want the Zaitsev product without wasting time drawing them all out. So what most students do is they'll draw one product, draw the pi bond here, draw the second one, draw the pi bond here. Let me know in the comments if you want to see a faster way, because who has time for that on an exam? Here's the faster way. Look at the hydrogen and look at the degree of substitution of the carbon holding the hydrogen. If this one right here is on a tertiary carbon, and this one right here is on a secondary carbon, a pi bond formed at the more substituted carbon will form the more substituted, more stable Zaitsev product. So all I have to do is draw a pi bond between this tertiary beta carbon and the alpha carbon, and I have my Zaitsev product, I have my major product, without having wasted time drawing anything else. When in doubt, draw them all and evaluate. But if you don't have time, identify the more substituted carbon, put the pi bond right there, and you're good to go. All right, up to this point, that was the easy stuff. Now I get to put my hands together with that evil, yeah. If you are ready to crank it up a notch, I want to see fire emojis in the comments for carbocation rearrangements, ring expansions, and pretty much full-on torture. But full-on torture that gets explained rather than just full-on torture for your exam. I see fire and firecrackers. Let's do it. With shortcuts. First, we'll have a molecule that looks like this. And we want, you know what, let's keep it simple still. What happens if I react this with H2SO4 and H2O? What am I dealing with? I have an alkene. That is the most reactive. It's reacting with an acid catalyst. The H2SO4 is only here to serve as a source of protons in solution. That is my acid for acid catalyzed hydration. And I know that I'm going to put an alcohol on the product. Now, this is a Markovnikov addition. And so the shortcut for a molecule, for a reaction like this, is you break the pi bond, you redraw the carbon skeleton, you identify which is your more substituted carbon. Well, this right here is primary, and this right here is secondary. And then for Markovnikov product, you put the alcohol or the nucleophile at the more substituted carbon. Except that does not work here because there's a trick. If you draw the mechanism, you will notice there's a carbocation, and then you will be able to do a rearrangement. But if you have to draw the product without the mechanism, here's what I want you to look for. If you have a known carbocation intermediate, even without drawing out any intermediates and any mechanisms, just look at this and look out if the carbocation would form on a secondary carbon near a tertiary carbon, you're going to have a hydride shift for a carbocation rearrangement. And that means I don't have to draw the mechanism to recognize. Immediately, I see the Markovnikov position is secondary. This right here is tertiary. The carbocation will go here. My alcohol will go here. And I never drew the rearrangement. What do you think? Pretty fast? Would you have gotten this right on the exam if you did not draw any kind of intermediates? Very fast is the key, because if you don't have time, you need a way to do it fast. But let's say you do have time. Let's say your professor says, show this step-by-step mechanism for this reaction, where we're going to react this right here with, let's do the same reagent, H2SO4 and water. This time, well, first of all, as soon as you see H2SO4, dismiss it. It's just a source of proton in solution. And then we have to figure out what kind of reaction it is. So what do you think? Easy, medium, or hard? Given that we have a leaving group rather than a pi bond, we're probably looking at substitution or elimination. So we'll go through the checklist real quick. We have our alkyl chain. That doesn't tell us anything because it's a secondary carbon. I am seeing multiple easies. Interesting. I am very impressed. I'm very impressed. Okay, so let's go through this quickly. I had a lot of requests for this, but I love that you guys are comfortable with this. All right, so alkyl chain doesn't tell us anything. We look at the attacker. We don't seem to have one. It's not the proton. It's not the H2SO4. This is another Solvent reaction. Next, we have the solvent polar and protic. It will stabilize any intermediates. And then we look at the leaving group, confirm it's going to leave. We are good to go. So let's show the mechanism. Oh, I didn't actually tell you what I was ruling out. Because it's water for solvolysis, it has to be a weak reaction. I'm not given heat. And so in this case, I could do substitution and elimination. I'm going to go with the SN1 product here. I'm not given heat, so let's go through it step by step. In the first step, the leaving group is going to leave to give me my carbocation intermediate. That is not what I'm trying to show. Let's put this one on the clipboard. There we go. I have my carbocation intermediate where the leaving group left. I recognize that I have a secondary carbocation near a tertiary carbon, which would give me a hydride shift, except here's the other trick. A secondary carbocation near, not a tertiary carbon, near a 5 or 4 membered ring is going to give us a ring expansion. And the reason is that 5-membered ring is not as stable as a 6-membered ring. And so we're going to take the opportunity where the carbocation rearrangement will be the entire ring opening up. And the way we're going to do that, let's draw it like this. We're going to look at this bond right here. I could have done the top or the bottom. I chose the bottom because in this case, it doesn't matter. It is symmetrical. Oops. No, I don't want to do that. Stop. There we go. This thing is trying to be weird on me. I'm going to take these green electrons and I'm going to shift them over here. Now, this is where a lot of students get confused and mess up. So I want to show you how I approach this. I do not go for the next structure. Instead, I redraw it exactly as I should see it. That is my new bond. I remind myself that this is where the bond used to be. The trick from part 1, remember the bond that lost, the carbon that lost something gets a carbocation. This carbon lost a bond, got nothing in return. That's the carbocation. This one used to be a carbocation, got a new bond. It no longer has a charge. And now that I clearly see what is going on, I'm going to number it and then redraw it. So I have 1, 2, 3, 4, 5, and 6. Now I don't have to look at it because I don't want to get confused looking at something and messing it up. I'm going to draw a 6-membered ring. I will number it in the same clockwise or counterclockwise direction. 1, 2, 3, 4, 5, 6. And then add all the things back in. Carbon 1 has a methyl group. Carbon 1 to 2 is where that new bond forms. So you can see that right there. Carbon 6 has a carbocation. And wait a minute, secondary carbocation near a tertiary carbon. Secondary carbocation, tertiary carbon, we're going to have a hydride shift. The hydrogen shifts over. That will now give me, let's draw it up here, a carbocation sitting right there. And in the last step, well, second to the last step, water will come in. Remember, this is solvolysis. The solvent can attack. This will give me, I'm going to redraw this. There we go. This will give me a water attached where oxygen has 1 lone pair and a positive charge. Another water molecule will come in to grab that extra proton, give oxygen back the electrons, and that will give me my final product with an alcohol at the tertiary carbon on a ring that I didn't actually start with. Love ring expansions. Yeah, these are a fun way to get points on your exam because if you know what to do, what I did here, the worst thing I can say for it is that it was tedious. It was a lot of drawing and just a lot of steps, but hopefully you didn't find anything difficult here because it made sense. When you're doing this on your exam, please, please put redraw because I have seen professors take points off and say this is not another step. know it's not another step. I just want to see it clearly because this right here looks drunk and falling on its face. Question, can you do a problem showing how you'd find a series of reaction if you're given the starting and ending molecule? Yes, I have synthesis problems coming up, so hold that thought. A couple of students did not learn that. Interesting. Is it below the methyl because of the backside attack, or doesn't matter? It actually does not matter because the carbocation is on an sp2 hybridized carbon. So that right there is sp2, trigonal planar, or simply flat. And if I have a carbocation here, it can attack from the top or from the bottom, where if the product was chiral, you would get racemic. But in this case, notice the symmetry going down the middle. That means it doesn't matter because the final product in this specific situation does not have any chirality. And what type of reaction is this? Well, technically, this was a combination of SN1 plus ring expansion, aka a professor favorite. So make sure you feel comfortable with this. Write it out a couple of times until the steps make sense, and you will just ace this on your exam. Question, why didn't you do a hydride shift? We did a hydride shift. Where did I show the hydride shift? Right here. This right here is the hydride shift. So this is my carbocation rearrangement, where the hydride, the hydrogen moved from the tertiary to the secondary carbon. The carbocation formed on the tertiary, more stable carbocation intermediate. And then I was able to add the water. What do I have, first of all? When we're looking at a synthesis, I'm given a reactant, I'm given a product. I don't want to start by looking and starting to react. I want to ask the two questions that I taught in the synthesis session. Question number one, what is the same? And in this case, it's the carbon chain. Question number two, what is different? And in this case, it's an iodine that went to a chlorine, which would just be, well, yeah, kick one out to get the other, except I gave you stereochemistry for the reactant, stereochemistry for the product, and I intentionally did not say racemic. The product has to be exactly like this. If I did an SN1 reaction, an SN1 has a carbocation intermediate. A carbocation is flat. That means I get top and bottom. I get racemic. SN1 will not work here. If I do SN2, SN2 wouldn't work here either because SN2 is an inversion of stereochemistry. I would have to have my group on the back. If I try to eliminate and get a pi bond and then do an addition reaction, again, I cannot control for stereochemistry because the pi bond is sp2 and flat. So first, do you still think this is an easy problem? Because I saw a lot of easy before. And aha, this is absolutely how I want you to think. Does it have to be one step? No, it does not. I can do this as a two-step reaction. So if I cannot do anything that has an sp2 intermediate, no carbocation for SN1, no alkene for an SN, for an addition reaction, what if I do a double SN2? Absolutely correct. If I take my starting molecule and I turn it into something that has a leaving group on the back, and then I turn it into something else, well, now I have an SN2 with an inversion of chirality, followed by another SN2 with an inversion of chirality, and it's just two SN2 reactions. And to clarify, I can't do an elimination here because the pi bond is sp2 flat, and that can get attacked from the top or the bottom. So now that I know that I can do a double elimination, a double SN2 substitution, the question is, how am I going to carry this out? Well, let's see. How do we get a chlorine onto a molecule? I need some kind of chlorine leaving group or chlorine attacker. And SOCl2 is a good way to control for getting the chlorine there and SOCl2 can kick out an alcohol. So what if I make this an alcohol by using something like NaOH in DMSO, and then SOCl2 in pyridine, I get an alcohol and I kick it out. SN2 SN2 a double inversion of configuration is a retention of configuration. All right, a couple of questions. So to repeat, SN1 will not work because SN1 gives me a carbocation. Carbocation will give me a racemic product. And if I did this with a carbocation, I would have some correct, some incorrect. And we want no side products here. Same reason for not doing an addition, because if I get an alkene, it's sp2, and then I add to the alkene, that can add top or bottom. Same thing with HCl. Question, how do you know that where did that question go? That SOCl2 can kick out an alcohol? An alcohol is a very bad leaving group. And so the way that you kick out an alcohol is by bribing it. I have two options. Option one with an alcohol is to protonate it. So for example, H2SO4, HBr, HCl, in H2O, I need a source of H plus in solution. This will give me an intermediate that looks like this, where I have an OH2 plus, good leaving group. That will give me a carbocation. And then from that carbocation, I can do whatever, depending on the situation. That is one way to get rid of an alcohol. Another way, if you want to control the outcome of the reaction, is to add something that will be big and bulky. So a couple of examples you will have learned would be a tosyl chloride in pyridine, SOCl2 in pyridine, PBr3. These are just different ways to make the alcohol into something bigger, bulkier, more stable, and then you kick it out rather than having it leave by itself. No carbocation intermediate, which is key because now you can control for the stereochemistry. This was a really good question. Let me know if that's clear. Pyridine is just the solvent, and specifically you use pyridine to avoid forming HCl, hydrochloric acid. Pyridine makes it a pyridinium chloride, which is just a mild solution. If you didn't learn about it, I don't know that you'd be expected to know it. So just look back through your professor's lecture notes, and if you don't have to know this, just ignore it. Can I use PI3? I don't actually know. I haven't seen that. Also, PH2Br2 or PBr. I'm not sure if that's a question or a statement. I don't know about PH2Br2. I haven't seen that, but PBr3 is definitely a good option. Question, what's the difference between writing a mechanism for the reaction or to write the product and show the transition state? A mechanism has all the arrows like we did here. Arrow, 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 like all the attacking arrows. That would be the mechanism. Intermediates and transition states would just be showing things like this right here. That's an intermediate. That's an intermediate, but without the actual mechanism. What about, speaking of pH, say you're given a molecule like this. You're not asked for the mechanism, only the product. What am I looking at with this? So we have NaOET and ETOH and heat. What do you think? First, do you think this is easy, medium, or hard? And let's evaluate. Anytime I see a leaving group, I'm thinking, am I going substitution elimination, or is it something else? If in the direction of substitution elimination, my alkyl chain Doesn't give me much because chlorine is on the secondary carbon. I look at my attacker and see NaOET. Anytime you see Na+, that's a positive spectator. That is just something that you ignore. ETO- is the negative charge hiding behind that positive spectator. That means I have a strong attacker. It is strong. It is not waiting for a carbocation. No SN1, no E1. Rule those out. So we're stuck now between SN2 and E2. Next, I move on to the solvent. I see that I have a polar protic solvent, which means I'm leaning towards elimination over substitution. And heat helps favor elimination over substitution because elimination has a higher activation energy, which needs the heat for a much, much more stable product. It's got a more entropically favored, is that the right word? It's got lower entropy. And that is why heat will favor elimination over substitution. So I know I'm looking at elimination. I have a good leaving group, so I'm good to go. The shortcut for an E2 product is to redraw the skeleton as you see it without the leaving group. And so if I draw it out like this, and I redraw my skeleton like this, I cannot put a pi bond here because this carbon has no hydrogen. There's nothing there to eliminate. So it's got to go in this direction. Does that mean that this right here is my product? Does this look correct to you? And to clarify, this is not an E2 major, SN2 minor. This is E2 major and SN2, no, not really. No, this is an E2 reaction. Polar protic solvent and heat are going to push it way, way in the direction of E2. And if you said this is not the correct product, you are absolutely correct. This is no good because that is where I want the pi bond. But when it comes to an E2 reaction, the hydrogen and the leaving group have to be perfectly lined up for the orbitals to collapse into each other. It's got to be straight dominoes. And the way I have this set up is absolutely not going to work. The reason for that is look at where I have my hydrogen. If that right there is a methyl group, my hydrogen is coming forward. If the hydrogen is coming forward and the chlorine is coming forward, that means it's like looking at a leaving group down here and the orbitals cannot do a U-turn. They have to go in the same direction, which means the only way to get them lined up anti-coplanar is by rotating the molecule. And so what I have to do is start with the skeleton on the left side of the molecule. That would be this carbon and this right here, like that. And then I have to rotate it. So the ethyl group goes down, the methyl group goes up. In rotating it like that, the hydrogen then goes down where the chlorine is up, and now I can put my pi bond here. So it's very, very similar, but you have to make sure that your hydrogen and leaving group are anti to each other. H and leaving group must be anti. If they're not, rotate. Question, when would you do the Hofmann product instead of rotating the bonds? Well, there's no option for a Hofmann product here because there's only one beta hydrogen, the light blue one. There are no other beta carbons with hydrogens, and so that's the only option here. Oh, whoops, where did it go? I'm a little confused on the stereochemistry with the wedge and the dash. Why did the CH3 lost the dash? Okay, so I think you're asking not about the rotation, but about this right here. And that is a really, really good question. So Justin, let me know if that's what you were asking. What I'm looking at here is an sp3 carbon atom. sp3 means that the entire orientation around that carbon atom is tetrahedral. It's three-dimensional. Things are coming forward, things are going back. They're just three-dimensional. But when I make a pi bond, that same carbon, this one right here, is now sp2 hybridized. And an sp2 hybridized carbon is trigonal planar. It's flat. Did I say trigonal planar before? I meant to say tetrahedral. I don't know what I said. This is tetrahedral, and this is flat. And because it's flat, I no longer have dashes and wedges. I just have lines in the plane of the page. So that was a very good question. Let me know if that's clear. Explain again why we have to rotate. When I eliminate for an E2 reaction, the way that this reaction happens is the orbitals, the electrons from the orbitals just kind of fall into each other, and they have to fall in a straight line. It has to do with the physics behind the reaction. And if you notice the way I wrote it here, see how this is lined up where the hydrogen is down and the leaving group is up? When the base grabs the hydrogen's electrons, these electrons collapse into the leaving group and sort of knock it out like a row of dominoes. The electrons have to go in that straight line. It has to be like dominoes. If you have a situation where the hydrogen is down and the leaving group is down, if the base tries to grab those hydrogens, the electrons go up, but these have to go down. That does not work. The orbitals will not line up to eliminate, and the leaving group will not get kicked out. And so you have to rotate the molecule. Right here, we have sp3. That means we have free rotation. And when you rotate, the hydrogen goes opposite the chlorine, the ethyl goes down, the methyl goes up, and then it's perfectly lined up like this. And that's when you can do the elimination. So that was a very good question. Let me know if that's clear. Justin, excellent. Destiny, I noticed you asked the same question, so let me know if that's clear. Orbitals are cool but spooky. Yeah, when I asked my professor this, it was my TA actually, he said, oh, don't worry, it's too complicated. I said, I get that it's too complicated, but I'm having trouble understanding. I need to see what happens. And so he took the time and showed this, or showed me something like this, and then it clicked. And I no longer need to know that whole orbital stuff that he taught me, but it helps the rest of it make sense enough to say dominoes. And dominoes is really the big takeaway, because ever since that clicked in my head, it made sense. You see a question about memorizing reagents. Go to layerforsci.com/memorize. I have a video on that, and I'll also put the link in the description. Let me just make a note. Okay, so that is the best way that I found to memorize reagents, mechanisms, reactants, just all the things that you have to know in organic chemistry. To clarify, rotating to ensure the H and the leaving group are anti. Yes, they have to be anti to each other. Exactly. How do we know which Cl is the leaving group? There's only one chlorine, and so I only have one option. All right, what about a problem that looks like this? And somehow, some way, you need to find a way to synthesize this. How would you begin a problem like this? When you see something like this, don't jump right in to what you see. Take a step back and ask the two questions. Question one, what is the same? This portion of the molecule. This thing right here is in both of them. So we'll just call it the green carbons. And then what is different is everything that was added. So let's carefully pay attention. We have a new bond from what we had to start to the new group. And the new group has 2 carbons. So we have to find a way to add 2 carbons and an OCH3, this piece right here. Now that we know where we're going, let's start breaking it apart. Because this is an Organic Chemistry 1 review, the only reaction that most students will have learned for adding carbons to the chain for chain elongation is alkyne. So we're going to stick with alkyne, but yes, absolutely a Grignard would be a great other method that we can use here. So where do we go from here? Identifying that we have to add 2 carbons and an OCH3, knowing that chain elongation via alkyne is the way we're going to go. Here's the trick I want you to recognize. As soon as you identify what had to happen, recognize that this right here came from the alkyne and it added to the rest of the molecule. So instead of coming up with all the pieces, I go this way and this way and this way, let's kind of take a big step back and say, somehow, somewhere along the line, I have a molecule that looks like this, where this is what I'm starting with. I have a new bond, and that new bond went to an alkyne. Now that is way too long. That new bond went to an alkyne. We'll fill this in after, but recognizing that this is how I got to a chain elongation is going to help me turn this into 2 problems, because now I have 2 easier problems. One, I got to get here, and from here, I got to get there. So how do we do that? When you see an alkyne and you identify where it attached to the molecule, break it up at that alkyne attaching to the molecule, give the portion that is attached a leaving group, and give this a negative charge. This is going to make it very, very easy, because one step back, what I have here is this right here with a leaving group. We'll give it a bromine. And then we have a new problem. How do I go from this right here to one that has a bromine? So instead of trying to do the whole thing at once, we break it up step by step. What reaction puts a bromine on a molecule that has nothing? This is what I call the something from nothing reaction. And the something from nothing reaction is a radical. If I don't have anything, I do a radical halogenation. In this case, we'll use NBS. N-bromosuccinimide is going to add a bromine through a radical intermediate at a carbon next to either a benzene ring or a pi bond. So we have that bromine on there. We then take this portion right here for the alkyne. That's how I'm going to add my 2 carbons. That's my acetylide. And now I have to figure out the second half of the reaction. So let's move this over a little bit. I usually like to do the reagents at the end, but whatever, we'll come back. So how do I go from an alkyne to an OCH3? I don't know. And if I don't know how to do that, I don't like to look at that piece, and I want to ask a different question. Knowing that at some point it came from an alkyne, what other molecule could I have used to react to give me this product? Meaning, form this product from something else. That something else could have been an alkene. Now, it doesn't look as familiar because it's got the OCH3, but remember the backpack trick. If I have an alkene and I react it, I can get an alcohol. The backpack trick is if I use an alcohol instead of water, I can get an ether, which I have in the product. I see a couple of questions coming in for NBS. NBS is N-bromosuccinimide, and this is simply a source of Br via radical. If you haven't learned it, just do a radical halogenation, but NBS is useful when you want to put a radical next to a pi bond or a conjugated system. And so looking here, alkoxymercuration, exactly. If I have oxymercuration, I get an alcohol. Alkoxymercuration, I get an ether. But let's not fill in the reagents just yet. Let's revisit this problem and ask, do I know how to go from an alkyne to an alkene? Well, yes, I do. It's just a simple partial reduction. And those are all my intermediates. I have nothing. Radical halogenation gets me a good leaving group. I attack it with an acetylide for an SN2. My chain grows. partial reduction to an alkene. I add an alcohol to get an ether. So let's fill in any missing reagents. To turn the alkyne into the alkene, because it's terminal, I don't have to worry about cis or trans. Those are just hydrogen. So I can use any of the partial reductions that I know. For example, H2 and a Lindlar's catalyst. Once I have the alkene, instead of oxymercuration, I can do alkoxymercuration. Oxymercuration is HgOAc2, H2O as step 1, and then step 2 is NaBH4. All I do is change it. Remember the backpack trick? If H2O is what I would use, but I want a backpack on there, a CH3, I just take that reagent and put a CH3. So I'll use CH3OH, and I get my product. All right, questions. Can we use NaH and an alkyl halide? On which step? I'm trying to see, because NaH is good for deprotonating something like an alcohol or an alkyne. Are you talking about this right here or something else? I'm not understanding the question. Can you go over the repeat unit? Okay, we're not going to do, I forgot the name, polymerization reactions. We're not going to do that today. For this one, I used the Lindlar's catalyst. I could have easily used dissolving metal reduction as well. Na and NH3, yes. So if I had to show how to make this, what I can show is an acetylene in the presence of sodium. No, wait, sorry, I'm mixing it up. You were asking about that one. This one I could have shown Na in NH2 in NH3. This one right here, if I did dissolving metal reduction, then I can use sodium in liquid ammonia. And I want to make sure we clarify the difference. This right here is an Na positive spectator, does nothing except balances charge. NH2 minus is the strong reactive base that deprotonates the alkyne. Here, the Na is not a positive spectator. It's a neutral, very reactive, strong radical, and this is a radical mechanism, or the way to get there is through a radical mechanism. Very reactive radical, spectator ion does nothing. All right, so let me know if that clarifies and if there's any questions there. All right, let's try. My professor used to love this one. Starting with any alkyl halide, 3 carbons or less, plus any inorganic reagent, synthesize this. First, if we're dealing with an alkyl halide 3 carbons or less, let's take a look at our product and figure out how we want to break it up. And if I can figure out how to break it up, the rest is very easy. Question 1, what is the same? Well, I have a total of 5 carbons, so I have 3 and 2 carbons. What is different is that I have to connect them. So again, alkyl halide 3 carbons or less, plus any inorganic to synthesize this. And what I need to do is figure out what I'm actually going to use. And so if I break it up, I'll take a 3-carbon alkyl halide here, make that the bond that attaches them, and then a 2-carbon alkyl halide here. I think that is the easiest way to do this. And so let's put our starting molecules here. We'll take this one, put a chlorine on it because why not? And then I'll take this one and put a chlorine on it because why not? Now I actually have a problem I can see. Does this make it easier to see what we're looking at? All right, how am I going to accomplish this synthesis? I like to get a general direction before I start. I know that this is a 3-carbon chain. I know that this is my 2-carbon chain. I see where I'm connecting them. But how am I going to connect them? In organic chemistry 1, you learned the alkyne 4-chain elongation. So we're going to guess that this right here, we're not going to guess. We're going to say that this came from an alkyne that I attached. And so like before, I'm not yet worried about all the little pieces. Let's go 1, 2, couple steps back and figure out where we would land with the alkyne there. So this right here, attached like this. Somehow, some way, I go from here to the final product. And then, as soon as I see very clearly where my alkyne is, break it, give this a negative charge, give that a leaving group. This right here is half the battle, because giving that a leaving group means this is ready to use as it is. And all I have to do is figure out now how to turn this into this. So let's go ahead and start solving for that first. If I want to make an alkyne from an alkane with something on it, I don't know how to do that. The best way to make an alkyne is from an alkene. So this is a pattern that I think I covered it in the synthesis exam, which if you haven't requested a copy yet, just type synthesis in the chat. I have the link somewhere. Yeah, put synthesis in the chat and I will respond with the link. Even if you're watching the recording, I want to make sure that you have access to the practice. The pattern to go from an alkene to an alkyne is halogenation, double elimination. So how do we do that? Well, first I need an alkene. No, I already said alkene, so we'll come back to it. We'll just show the alkene. From the alkene, we do a halogenation. So we put 2 halogens on it. And then we do a double elimination to give me the alkyne. And then from the alkyne, we can very easily get to this by just attaching it. So let's hold this thought, keep this right here. The one step we're going to need here, let's squeeze it in, is turn the alkyne into an acetylide with a negative charge. Let's come back to here. How do I go from an alkyl halide to an alkene? That will just be a simple elimination. So I have my first path. It's a lot of steps, but here's the thing. Instead of memorizing, I do this, I do this, I do this, I want you to see this pattern. Alkene to alkyne, you simply go through a dihalide in the process. This is a reaction I want you to practice so many times that it's just, it's reflexive. I have an alkene, I want an alkyne, I add a dihalide, and I'm good to go. Then you go from the alkyl halide to the alkene. That's a plain old E2 reaction, something you should know by now. Now that we have this right here, I need a little bit more room. So we get this right here. We simply add this piece to it. So now it's beginning to look like a mess. So let's fill it in. If I have this right here and I react it with my starting molecule, then I get this. And now the question is, how do I go from here to here? If all I have is an alkane with nothing on it, I could just do a straight up reduction and I'm actually good to go. So that second part was pretty easy. Look at that, guys. We have another A minus on the course. Congratulations. That is awesome. And I love hearing these, like hearing that you're doing well, because I make the videos and I hope you learn and I want you to understand that you have to take the time and put in the work. So the fact that you did and you got an A minus, congratulations. That is awesome. I'm so proud of you. Oh, where did that go? Can you use H2 and excess palladium carbide? Yes. So let's go ahead and fill in the reagents. H2 in a metal catalyst like palladium carbide. And let's go forward and fill in the forward reaction from the beginning. From the alkyl halide to the alkene, this is a regular elimination. So we're going to use any strong base. I'm going to choose NaOH and H2O. Once I have the alkene, we've already seen this reaction, Br2 in something like CCl4. Where am I putting it? That goes here. That will give me the dihalide. Once I have the dihalide, NaNH2 in NH3 liquid. I don't actually need to show this as a separate step. And the reason for that is when I react with NaNH2 and NH3, it has to be in excess. In addition to the double elimination, the terminal hydrogen also gets pulled by another base, and so it immediately goes to the negative, the acetylide. I add this in, another starting molecule. This is just an SN2 reaction. And then I reduce it. And there's my final product. So hopefully, after going through not just the problems today, but a lot of the explanations behind the problem, I hope that you feel a little bit stronger in reaction patterns, in what you have to do. Anything that was not clear, use this as a guide for, hey, I need to go and study this topic or that topic. So instead of just being overwhelmed trying to do everything, now you know exactly what you have to work on. For a copy of tonight's session notes, sign up at leahversailles.com/orgolive. You'll also get the notes from part 1. This is part 2, so you'll also get the notes from part 1 and so much more. For more practice, or even more practice, in case you haven't had enough, make sure you try the exams that I mentioned earlier. Just comment which one you want. So right now I have 2 brand new exams from this semester. I have a substitution elimination midterm. It is a whopper of an exam. I think it's like 4 or so pages of SN1 versus SN2, E1 versus E2, choosing between them. So just comment substitution or elimination, or anything that tells me that's the exam you want. And then the brand new exam on synthesis, retrosynthesis, and multistep reactions. That's the other one that I just finished, actually last week. Just comment synthesis and you'll get that one as well. Yes, even if you're watching the recording, I make an effort to go back to all the comments on my YouTube channel and I'll make sure you have the link.